Welcome to PTP Take 3, a Leader and Arista seminar. Gerard Phillips, Steve Holmes, and Kevin Salvidge are back with the third live PTP webinar, but this time you're in control because we took your questions and that's what's happening. And today they'll be answering your questions around PTP and SMPTE 2110 deployments. And between the three of them, they are unrivaled in terms of the real world experience. And they've got this personal experience they're going to share around best design, configuration, and just avoiding pitfalls. So over to you, Kevin, Steve, and Gerard.
Thank you, Cindy.
Thank you very much. So Steve, we're back again. So for all those who saw us at IBC, we told you we'd be back. And
we are definitely.
And we're very fortunate this time we've been joined by Gerard from Arista. Gerard, would you like to introduce yourself for the one person on this call who doesn't know you?
Yeah, sure. Gerard Phillips, I'm based in the UK, work for Arista Networks. I'm a systems engineer, but I'm also a media and entertainment tech lead, which means I focus on helping broadcasters move from SDI to IP in whatever form that may be, making sure that those transitions kind of work well. And, you know, one of the big things in the 2110 world is PTP. So that's also one of my kind of specialities.
Excellent.
So pleased to have you, Gerald.
Thank you.
Thank you.
So as we said, we'd like to thank everybody for the questions. We've got more than we're going to get through in the next hour. So we have consolidated, coerced, and everything like that. So we try to put them into common themes and that. And we're going to start off with kind of under the title of things to consider when designing your PTP architecture. So you've got a blank sheet of paper. You've heard all the horror stories and all the mistakes other people have made. How do you not fall into those traps? Yeah. And we'll start off with the first question is, what is the most common system design error?
Go ahead, Kev.
So, Steve, personally, one of my bugbears is people not changing the default domain from 127.
Yes, I would agree. I mean, because virtually every PTP device gets shipped, especially all the generators get shipped at 127. And that is an issue because any new device you put on your network, if it is 127, I've seen multiple cases of things go rogue because they put a new device on the network and it decided to take over. And your PTP went wonky because a device went on the network at 127, and that happened to be where you were. You didn't get a chance to put it to your domain.
And there's one, so we're not going to use 127, we're going to change it, but there's one other domain not to use as well, isn't there, Steve?
Yeah, it's good to stay away from 0 also, only because that's AES67 and Dante. It's an audio domain, and it's just best not to go there from a design perspective. It's just a good best practice. Gerard, any question?
Yeah, so I mean, I think they're both good. They're both good kind of bits of advice. I would say you can kind of mitigate against the whole kind of rogue device on your domain, either by moving away from the default domains, which you should probably be doing, but also by using, you know, the kind of capabilities in switches to tell the switches to only lock to preferred grandmaster IDs, or to use things like PTP role master, which prevent host-facing ports from taking part in any form of BMCA and forcing them into a time transmitter or a leader mode. I'd chuck in another couple. I think architecturally, and we'll cover this a little bit later, architecturally, there's some really good best practices, and there's not really much excuse for broadcasters to go out and reinvent the wheel. There's kind of pretty well-defined ways that the industry is rolling out PTP everywhere. So not educating yourselves, or not listening to a good system system integrator, or not talking to your network vendor maybe is a thing to try and avoid. Announced message intervals, that's another common kind of not having those match between follower and leader is a absolutely surefire way of falling foul of PTP not working as well as it should do. And then I guess I'd say having a proper understanding of how the priority one works, for example, to make sure that in your failure scenarios, the things that you want to be in charge actually remain in charge. Those would be some of the things I'd be thinking about.
The next one that's popped up is what considerations when determining whether to use boundary clocks versus transparent clocks? Gerard, I think this is your one.
Yeah, so I mean, 99% of the time, my strong recommendation would be to use boundary clocks versus transparent clocks. They both perform the same basic function of reducing the jitter component of traffic through the network or the PTP traffic through the network, which then causes uncertainties and for the endpoints to not be able to lock as effectively or as accurate as we'd like them to. Boundary clocks have got a whole stack of benefits, which I think make it absolutely my preference. So, for example, if you're looking to scale a big system, boundary clocks essentially slice the problem into lots of smaller blocks. You don't end up with grandmasters having to serve potentially hundreds of thousands of endpoints. You don't end up with endpoints seeing everybody else's delay requests, everybody else's delay responses. So in terms of network scale, host capability, boundary clocks kind of remove all of that problem. As I was just talking about PTP Role Master, that kind of gives you a massive ability to build security. So only the right GMs or any GMs that are in the right places will be able to talk to your network and become leaders. And visibility. I mean, certainly in the Arista world, I can't speak for anyone else, but once you're in a world where you've got boundary clocks, you've got an awful lot of telemetry and visibility that is now built into the system for you. You can see packet counts, drop packets. You can really get a lot of understanding of how well the system is locked globally. So in our world, unless you've got a really unusual use case, boundary clocks all the way for me.
Yeah, I would agree with that 100%, especially like you said, on large systems, you can swamp a grandmaster with messages because it's PTP is pretty verbose and you'll get a ton of messages and you hit a point where the grandmaster cannot talk anymore. And on large networks, you're going to get enough just feeding the boundary clocks themselves. So yeah, it really segregates that out very nicely.
And from personal experience, Steve, we've seen that, and it wasn't on a very big network either when it happened.
Yeah.
So
and you have the ability to ask endpoints to produce unicast delay requests, but then you've got to configure everything. You've got the ability to turn off management messages. If endpoints are well behaved, then they'll not create multicast acts to management messages, but they're not all well behaved. Those kind of extra load, it's not a big problem for the network, but it becomes a big problem if it's being delivered by a transparent clock to everybody else in the network. Audio devices, they're DSP heavy and CPU light. So if you throw, thousands of extra messages at them, you've given them a real headache. So I would definitely boundary clock at the edge. And once you've got boundary clock at the edge, if you start to try and build mixed systems, you've really made your life very difficult.
Yeah.
So moving on to the next question, which is sort of along the same lines, how to architect PTP switches, boundary or transparent, and how to determine end-to-end versus peer-to-peer between clients and switches and clock sources.
Yeah, that's a good one. I mean, if you can flash up my slide number 2, it's a kind of that would be our generic and entirely standard PTP architecture that we deliver everywhere. So what you'll find is if you think about delivering it as boundary clocks top to bottom, so from the GMs through some distribution switches, they're typically there because you need to change the speed of the GMs from maybe a gig or 1 gig up to 40, 100, 400, whatever the spine happens to be. And then if you push that down, so you see also we're delivering the same clock to both red and blue, or amber and blue. That's also a recommendation. It simplifies things. If we get around, we have enough time, we can cover that in a little bit more detail. The kind of end-to-end or peer-to-peer question is a good one. It kind of doesn't, theoretically, it kind of doesn't matter in a boundary clocked environment, because every link is a peer-to-peer link, if you like. There's a leader at one end and a follower at the other end. So there's no big difference functionally between those two in a boundary clocked network. But bear in mind, 2059-2 has been around for a long old time, and I would say 99.999% of endpoints support end-to-end. They don't really support peer-to-peer. And so whatever you choose to do, you're going to end up with an end-to-end architecture at the access layer. And so you may as well build that everywhere else. So top down, this sort of 3-layer architecture works very well. And end-to-end, please, and boundary clocks.
Yep.
I can read the question. So is it possible to find all the necessary equipment products as IP for full IP systems for PCR and MCR applications in the market? So this is kind of not really, it's not really a PTP question, but I mean, the answer is yes, because there are hundreds and hundreds and hundreds of 2110 systems out there, whether it's live production or master control. So yeah, if you choose well, you'll be able to find hundreds of products that
for your particular application. Most of the time you can get it from one vendor, but you may have to mix a couple vendors. But I have seen 100% 2110 networks completely online with a lot of channels running that run absolutely perfect. And they are 99.9% 2110.
So the next question that's popped up, PTP deployments used to take a lot of time. So who asked this question? Patrick came in. I remember when Meinberg PTP TrackHound came out, that really helped people visualize the PTP traffic and speed up packet capture. What improvements have been made since, and how much time do you allocate to PTP architecture today? I mean, we're sitting here as a test and measurement manufacturer, and that's one of the things we analyze and monitor. And Gerard, you have a number of integrated tools within your products that are also monitoring the health, haven't you? Of, the PTP packets that are flying.
Yeah, exactly. So I was going to kind of there's a few parts of this question, isn't there? So I was going to kind of start with the how much time do you allocate to PTP architectures? And I'd say I personally don't allocate a lot of time to PTP architectures these days, because the best practice, proven best practice, customer delivered, operational, running now best practice is pretty well documented. I mean, I'd like to think that we will follow up everyone's email, questions with, and we'll be able to add a bunch of extra links to resources, perhaps. So that there are a number of really good webinars that have been done that talk about the architectures that you can use, and that will really limit the amount of time you need to spend worrying about PTP architectures.
Yeah.
In terms of monitoring, there's a ton of amazing information on the switches. That information can be streamed to Arista's own monitoring tools, CloudVision, for example, or it can be streamed to other third-party tools, like, for example, Providius has got quite a nice tool, and Data Miner can help to visualize some of this stuff. And of course, Kevin and Steve will talk about how you can use their amazing products to monitor PTP pretty accurately.
Yeah. Well, and the placement of boundary clocks kind of gets in the middle of what TrackHound can do too, because that segments the network out so they can't see. If they're sitting on the endpoint, they can't see back behind the boundary clock. And if they're sitting back on the leaf spline, they can't see out to the edge. So it's
that is a really good point, Steve. And I guess maybe I'll jump back in a rude fashion and say, I mean, SMPTE's kind of spotted that that's a problem potentially. So there is a 2059-15, I think that's right, which is some work to deliver a Yang model that could be used to deliver PTP telemetry in a standardized form from any part of the network and any end host. So that if that came to fruition, that'd be quite cool. That would be then a standardized way of receiving telemetry about PTP. It kind of goes back, if you're running boundary clocks, which you should be, it goes back to the fact there is an awful lot of telemetry you could be using. And if the industry moves, as our objectives are to move to PTP 2.1, then some of that telemetry availability is kind of built into PTP version 2.1 as well.
Yeah. So we sort of touched a bit of next question about monitoring. So how can PTP be monitored on every boundary clock? Any good PTP real-time monitoring tools? I think we've touched on those. And what is the single best fault-finding kit that you can use to resolve PTP issues? I mean, you're looking at a combination of analysis tools, between your switch manufacturer, between your test and measurement manufacturer. You're getting a 360-degree view of what's going on with your PTP. There's probably no one tool that's going to every time give you the answer, but you look at the results from a combination. And the other probably vital thing here is to watch it over a period of time, because you're looking for trends. You're looking for it gradually creeping up or creeping down. You want to address those issues before they become a quality of service issue on your network. So my personal opinion is it's a combination of them. I sit here in my office. I'm fortunate to have both the Leader and Fabrics products running, and one I use for one I use for another. It's like that. You'll get to know which tools suit best your network, how you access them remotely, and all of those sorts of things come into play here. So
if the question was how do you monitor each boundary clock, then the answer is that Arista boundary clocks have got an awful lot of telemetry. And I did this test quite a long time ago, and it shows the kind of error distribution, offset from master distribution, if you like, on 3 layers in the network. So that the top middle is at the PTP distribution, the bottom left is at spine layer, and the bottom right is at leaf layer. And that graph was just built up over a couple of hours from looking at the offset from master, reading that out, looking at that telemetry and plotting it out. So, and to answer the question, there's a ton of information available about the behavior of the time receiver port in a boundary clock. So what used to be called the slave port, what was kind of going to be the follower port. So that information does exist within the switches, and then the question is how do you extract that, and how do you visualize it? And you could do it yourself. You could use Grafana. You could use any number of professional tools that exist, as I say, from people like Dataminer or Providius, or many of the broadcast control vendors also will show you the kind of PTP quality within the network. So there's no shortage of methods of doing exactly the thing that's being asked.
The other bit I'd say to people is get to learn what's going on with your system. Get to understand what the different measurements are, what the spread of packets and things like that, so that then when you do look at things and things start to change, you think, that's not what it was yesterday, or that's not what it was the day before. Why are my packets now being
when your network's up and running, there's what I like to call kind of a signature that your network will look like when it is healthy. And you get to learn that signature of what these graphs look like and what they look like when it's not healthy. And you're looking for those types of changes. It's the same thing when we're looking at, min-max packet spread out of a server. Every server's got its own transmit signature, and you learn what that transmit signature looks like. And when that signature is not healthy, it's a change from norm.
Yeah, and I mean the two things you're typically measuring from a boundary clock is the offset from master, which is how
Yeah.
wrong do we think our clock is, and the network latency. And so any measuring tool that can give you a good view of that, kind of an instantaneous view of that, and a longer term view of that, will help you to understand whether the boundary clock is behaving properly. So offset from master in a good network is going to be plus or minus 50 nanoseconds, and it should not be, that is achievable. So a good network switch will allow you to be alerted using syslog or some other sort of telemetry if you are starting to see offset from master being beyond a certain number. So you could say, tell me if offset from master is bigger than 250 nanoseconds, please. At that point, you can start worrying about it. And then the network latency, if you monitor the network latency, what you should discover is it's kind of irrelevant what it is. It'll depend very much on your media type, the transceiver type, the speed of the link, but it should not vary by more than 2 or 3 nanoseconds in the way it chooses to measure itself. And if it does change, that is assuming you got point-to-point boundary clocks, which is what you're aiming for, that latency is a constant. It's the speed of light plus whatever it happens to be through your optics to get you in and out of the ASIC. So if you can monitor those two things, you have a pretty good chance of being very confident of the health of your network.
Excellent. So moving on down. So how do you deal with ensuring time is accurate across leaf/blade switches from different manufacturers? Perish the thought that somebody would buy different manufacturers' products.
Well, yeah. So the answer to this one's easy, right? I mean, PTP is a very well understood standard, and assuming that all the vendors have built PTP to the same standards, the whole point of PTP is that it delivers time and it takes out any differences or takes out latency in the delivery of those packets. And so assuming that you've got point-to-point boundary clocks everywhere, what you'll end up with through a well-designed network with well-behaved boundary clocks is clocks at the end that are plus or minus 50 or 100 nanoseconds of each other, and they will deliver that day in, day out.
Yeah, it's part of the sync mechanism that's built into PTP. It removes whatever latency there is in the entire network structure from what the grandmaster put out to what was delivered, and the end product is handed a number that says, hey, subtract this off of this and you have exactly what was put out by PTP.
Yeah, the sync message and the delay request, delay response used together, you can calculate the network latency.
Yeah.
And once you've calculated that network latency, and as long as you're talking about a well-behaved boundary clock to boundary clock, then that network latency won't change. And what that means is that once you've stabilized your calculation for network latency, you can essentially take that number off the sync time message you receive, and that is the time that it's supposed to be. And so internally to each device, you'll have essentially a PLL, which is running a trained and an in-trained clock, which is the same frequency and is phase locked now to the upstream grandmaster. So the only time that's going to go wrong is if that latency changes. But we're talking here about point-to-point boundary clocks. I got to tell you, I've had a couple of questions internally at Arista over the course of the last few months about how far what's the distance I can lock a boundary clock to another boundary clock over. And in our world, at least, the answer is at least between London and Washington. So we have a customer who's put in a dark fiber between London and Washington, and it's a point-to-point connection, and we have a boundary clock in Washington locked to the boundary clock in London, and it's plus or minus a few hundred nanoseconds. Absolutely cracking stuff over a latency of whatever the speed of light is over a few thousand miles.
Yep.
We did briefly just mention, Jim, that we've had a question here about allowed jitter for 2059-2, and 250 nanoseconds was mentioned and more. So there is actually no spec. I mean, there used to be a number in 2059, but it's kind of been taken out.
if you think about it, you're looking to get these things aligned. You're looking to get endpoints aligned so that they can take pictures at the same time and take audio samples at the same time, and then deliver audio samples to speakers and deliver frames to displays. And consequently, from the the PTP being turned into RTP, you can choose to mix the right signals together in the processing chain. So in reality, if you kind of do the maths on 48 kilohertz, then a microsecond is good enough by a long way. But in general, you ought to be seeing, on a well-behaved, good GM, good connectivity, good switch network, you should be seeing plus or minus 50, plus or minus 100 maybe. So you could definitely choose to alert at 250 if you wanted to. I think the big issue here is, not big issue, but the biggest thing for me is different vendors have made their endpoints more or less sensitive to different amounts of PTP jitter, and those are decisions that endpoint vendors have made. And so you will need to build a network that's good enough to accommodate your most picky endpoint, and that'll be part of a POC or something like that.
Yeah, and it's like testing SDI receivers. There's no two SDI receivers that are going to fall off the cliff at the same exact point. There is no specification for the sensitivity of that SDI receiver. Same thing goes here. It is up to you to test, to know what devices you're putting in your network and what their tolerances are, and know when you need to think about things.
We've discussed this in the past, and having a proof of concept or an engineering testbed system is going to be your best friend.
Yes.
But it's going to allow you to put different devices on, do software upgrades and all of that, and then have confidence that new endpoints can be plugged onto your network. You can do software upgrades without then having to do regression back if it doesn't work. So that's one of the things we've emphasized this in the past, but build yourself a testbed system, because it will be your best friend as you go forward.
For loads and loads and loads of reasons, right? I mean, you want to update the software on the switches, you should do that in the lab first. You want to update the software on your endpoints, you should do that in the lab first. You want to change an architecture, do that in the lab first. You want to run you want to build a playbook for disaster recovery. Well, you would definitely want to do that in the lab first, right? If you want to try some automation, you should be doing that in the lab first. So I would, for bigger systems, I'd be recommending that you buy a lab up front and you build it, and then use that as part of your process to decide exactly what to build in reality. But then you continue to keep that up to date, and you use that as your real hardware digital twin of a system that you roll out all sorts of stuff before you roll it out into your production network.
And it's great also for training new members of staff who come on board, getting them familiar with it. They can see what happens when you pull things out and they drop and die, and how you recover. So it's your best friend. So you sort of touched on this, incorporating Stratum 1 devices across PTP-aware switches. Also the relationship between multicast and PTP, especially when VLANs and routing between VLANs is concerned, e.g. breaking out audio onto an AS67 or a Dante-specific VLAN. They are somebody's, I think, has got personal experience there asking that one.
That is a fab and wide-reaching question, isn't it?
Yes.
So I mean the Stratum 1 clock is a great question. I mean, there's nothing to say that your grandmasters have to be locked to GPS. I mean, there's many ways that you could entrain your grandmasters. GPS, GNSS is just one of them, really. There are plenty of grandmasters that allow you to lock them to a PPM, a pulse per minute, PPS, a pulse per second signal. So maybe you've got a really accurate clock that's creating PPS, or maybe you've got a cesium clock that you're using, which has got a built-in PTP mastering capability. So I often see, or perhaps you want to lock yourself up to sync E. So maybe you're going to have synchronous Ethernet delivering your frequency, and you're going to use PTP to determine your time of day and phase. So there are plenty of organizations who have got really, super accurate clocks, which they use in they have a very small network where they then deliver an absolutely master version of PTP to a series of then secondary grandmasters that are then locked to the upstream clocks, but then deliver out to different segments of their organization. So I think Steve can probably talk about, I think we talk a little bit later, we've got a question a little bit later about synchronizing PTP and Black and Burst together, but it's a very similar concept, right? Creating a series of tiers of clocks that are enabling you to have some incredibly high precision clocks that are being used to entrain your other lower layered clocks. So can it be done? Yes, it can, and it definitely is being done. The kind of relationship between multicast and PTP and VLANs is that's an interesting one. And it sort of goes away if you build boundary clocks, if you use a boundary clock architecture. The requirement to kind of consider PTP as multicast and route it is only really applicable if you're building a network out of transparent clocks. As soon as I suppose it's one of the things I should have said earlier, simplicity, right? I mean, if you move to a boundary clocked environment, you don't have to build any multicast delivery for PTP because it's just dealt with as part of the boundary clock. And then you are in a world where you can break out different messaging rates for different hosts, different messaging rates for different bits of the network. You may not want to use AES 67R16 everywhere. You may want to use lower rate messages for some audio devices, and you may even want higher rate messages for some other more picky devices. So boundary clock is definitely in terms of flexibility and segmentation is definitely your friend. And we'll come back and touch on some other bits and bobs to do with audio networks as we head through the questions.
We've got a question here about maintaining PTP timing between domains and it being a challenge, and that some operators still prefer to use MPEG-2 transport streams in contribution so that timing is maintained. Here we are, 2025 almost, an MPEG transport stream still. Steve, I think they were around when you started, weren't they?
Yeah. So, transport streams are, asynchronous, or there really is no synchronization per se in them. There's a PTP or PCR clock, but I'd say 3/4 of the receivers completely ignore the PCR clock. It's clocked on receive in. You generally have to turn around, put it into a frame store, reset it based on your local clock. So, you're going to have frame syncs at the end. But honestly, not a lot has changed even in 2110 delivery. The world still sits there, and we still have to deal with the delay that you get in fiber. Fiber has the almost exact same delay as a piece of coax has. So something that's time stamped at an origination is going to show up 100 kilometers at the receiver about a third of the way through the frame that the same timestamp was created for. So you can't just put things in. I mean, yes, it will be stable, it will be accurate, but there's no way to move time backwards.
If we could. So does this mean 2022-6 might be?
It's 2022-6 is great for this, and it's something that we were talking about with Gerard, is everything is put together and you can't have different delays. You can't have packets get lost, routing issues. Your video, your audio, your ANTS data is together. It can't move. It will be delivered exactly together in time with each other. And nothing happens, and then you can split that back out to a 2110 network if you do need to manage audio, video, and ANTS data separate. but it's a gorgeous way to transport things.
Yeah, I think there's definitely there's loads of angles to this question. One of them is this idea of the extra pain that 2110 separate essences brings to synchronization of stuff across a WAN, for example. Certainly, if you're talking about a contribution or distribution type feed, then they're likely to be different organizations. So you kind of want to find a way that ensures that when somebody sends it, QAs it, they know that it doesn't matter what happens in between. It's going to, as long as the packets make it, they're good. So I think kind of non-2110 type stuff like MPEG transport streams or 2023-6 or the work that the VSF's ground to cloud to ground work is doing to encapsulate or wrap up bundles of essences. I think they're spot on. So that's kind of like the kind of taking the timing problem away from sending bundles of essence. I think that the other question, the other point you raised, Steve, is a absolutely spot on. And it's no different to it has ever been, is exactly what you're saying, right? I mean, you have a load of data, you send it co-timed with PTP at one end, and surprise, surprise, it takes some time to get there, whether that's, a microsecond or a millisecond or 5 milliseconds, it doesn't matter actually. What you're going to have to do at the other end is resynchronize it into the world you wish to work in. Now, whether it may well have been frequency synchronous, but it's no longer phase synchronous. So you're going to have to fix that in the same ways you'd have had to fix it before. And then the third thing I wanted to throw in is one of the things I've been starting to see recently, which is it's taken me a little while to get my head around it, but when you send in this world, when you send flows from one end of a link to another end of a link, you're obviously describing that flow with an STP file, and that STP file has got a TS clock ref, I think it's called, in it, which describes which clock this flow is synchronous to. And if you think about it, there's only two use cases: that the flow is synchronous to the place it's received at, or the flow is not synchronous to the place it's received at. If both ends are locked to a traceable clock, then the easiest thing is to say this is a flow which is locked to a traceable clock. And then the other end can see that and understand that if they've got a traceable clock, then they can just synchronize it as they normally would. Pretty much anything else in that packet is going to say, oh, it's got a clock, but I don't know what it is, and it's not synchronous to mine, or probably isn't, or may not be. We don't know. And at that point, you're going to have to throw in a much more flexible frame store than a retiming frame store. So I think, but how the endpoint receives that, I think this is kind of, we're all learning about building these much bigger systems. And one of the problems is, as we talked a little bit earlier about how some endpoints are more sensitive to PTP jitter than others, some endpoints are way more sensitive to the STP files not containing what they're looking for than others. So these things are things that can work, should work, but you'll have to play with it and see whether it does work in the kit that you're planning to do it with.
Fantastic. I'm going to take one more question from this section, because this is one that I've come across now quite a lot. What is the best way to manage PTP version 1 and PTP version 2 when forced to use a mixed 2110-30 and Dante audio workflow? So for those who are not familiar, PTP version 1 and PTP version 2 are not compatible. And I think we're seeing more and more people who have audio over IP systems now venturing across to looking at doing video, but obviously wanting to retain their audio workflows.
Yeah, who do you want to take that one? I'll happily take that.
You want to start that one off, Gerard, and we'll.
Yeah, I can start that one off. So there's two things in there. So we're talking about kind of 2110 system with AES67 or Dante type use cases. So in many cases, you can reconfigure PTP version 1 devices to run PTP version 2. So see if you can do that to start with. If you can't do that, then these systems have historically run across non-PTP aware networks. And one of the things that you can do in a boundary clock system is you can ask the boundary clock system to forward PTP version 1. So continue to deliver PTP version 2 as you would normally expect, But if there is a grandmaster that's running PTP version 1 in the system, we can happily forward that traffic through a boundary clock as we would have forwarded it before. So still not dealt with in a PTP friendly way, but delivered to the endpoints. And typically that works pretty well. The other thing to consider is often, and Steve raised it at the beginning, right? Often audio devices really want to be in domain 0. And that's a domain that we're not looking to. So if, for example, you are running a system where you've got this all PTP version 2, but you've got a little island that wants to be a domain 0 and the rest of yours wants to be domain 128, for example, then what are you going to do there? Historically, you would have had to put that through another boundary clock, where a back-to-back boundary clock where you could, or back-to-back, receiver sender where you could translate the domain. One of the things that Arista's done recently is it's added per port PTP domain capability. And what that means is we could be running 128 for the 2110 network. And then where we hand off a clock to a Dante enclave, we essentially NAT the domain to domain 0 to enable you to, so in the case where you can run it all on V2, you can now deliver non-core PTP domains to other users, and that could be audio devices, or it could be an OB truck that's just docked, right? And you don't want to change its PTP domain because you don't want to tinker with its config, but you can deliver whatever it is that they want.
Yeah, and a lot of the audio networks where Dante is separate from what we're dealing with from 2110. You can take PTP V2. There's a lot of Dante products out there that'll take V2 lock on one side and provide V1 for Dante on the other side, so that it is still clocked to your grandmaster, but it's one way to get there. Also,
if you can kind of collapse these networks down, these PTP networks down, it's well worth doing, because there's not very many devices that will allow you to run more than one domain within the network. And if you absolutely need to do that, then you're in the position that you're going to have to start running transparent clocks, because they of course don't care about the domain. They're just pushing packets and updating the correction field.
Yeah.
So transparent clock network will allow you to run as many domains as you like, but then you're back to all the problems that we discussed earlier about scale and visibility and endpoints. Endpoints are now receiving 14 PTP domains. Can they cope with that? Have they been designed to deal with receiving more than one set of domains?
Yep. Next question.
Right. So let's move on to the subject of hybrid IP and SDI environments and how PTP and Blackburst and tri-level sync can coexist. Now, we have done a whole session on this one, Steve. So for those who haven't, I'd recommend visiting our YouTube channel and catching up on that. But for those new to it, Steve, what are the key points that you would recommend? Because let's be honest, nobody has a completely IP facility. Somewhere in there is that one device that's got SDI and it wants Blackburst or tri-level sync as a reference.
Yeah. Well, I've seen 2110 devices that were deriving what they were doing, and they were still locked to black to get their 2110 to work. But the biggest thing that you want to deal with is in your grandmaster is to have a sync pulse generator that generates everything you need that is locked to a single oscillator that is an oven controlled oscillator that may be locked to GNSS. It may run free. It may be locked, like Gerard said, to 1 ppm time, whatever it's locked to, but everything is derived off of that single oscillator. That way your black, your PTP, your SDI test signals, your all your AES, stars, black, whatever, is all coming from the same oscillator, and they can't be not locked to each other. They can't drift. There's some devices out there that if GPS is there, everybody's absolutely perfectly happy. But as soon as you lose GPS, they all go to their own internal clock, and your PTP is doing one thing and your Blackburst is doing something completely different, and they just start drifting away from each other. It's just critical that your sync pulse generator run off of a single oscillator that feeds everybody. So everybody, regardless if it's on internal or sync to, whatever your master sync source is, Blackburst, whatever, that everybody is perfectly in time with each other at all times, regardless of any catastrophic things that happen within the synchronization network.
I think that leads us into the next question. People are saying, is it necessary to have a GPS connection on these systems?
Not at all. It works absolutely perfect. The only difference is the clock class at which PTP will be generated will be lower. You get clock class 6 if you're locked to GPS, 248 if you're sitting on internal, and that's just the quality of the clock itself, how accurate the absolute clock is. So you can see from that GPS is going to give you a far superior accuracy, because we're down in the nanosecond range, versus looking at Blackburst or looking at even a 1 ppm clock that's an internal oven controlled crystal. But they work perfect. That oven controlled crystal, we have TV stations that run the entire TV station off of that forever, and it works perfect.
Next one, we sort of touched on this. Must you use the same PTP clock for both your red and blue 2110 networks? Now, I know this is a contentious one.
Well, I've had some talk with some people, and if you think about it, because of the way the receivers have the packet picker in there, there's one processing device in the receiver. It's getting 2 networks fed to it. The networks go into the packet picker, and whichever packet shows up first is the packet that's delivered to that receiver. And if you have 2 different domains, especially, you're going to hand off, just depending on red or blue, 2 different domains, and it's going to be switching domains all the time on you. And receivers typically only lock to a single domain. You're going to drive that poor receiver bonkers. And you're changing MAC addresses, even if they are perfectly in time with each other and the same domain, you're going to be changing MAC addresses every time it switches back and forth. And there's a lot of receivers that once they see a MAC address change, they completely relock. They should.
I think that's the key thing here, isn't it? I mean, neither 1588 nor 2059-2 or 2110 specify how an endpoint should behave with. I mean, there's work in progress, but there's nothing that defines how they should be treated as 2 independent clocks as far as 1588 is concerned, 2 independent receivers. And the problem is, because there's no there's no expectation that the endpoint essentially does BMCA and chooses the best master clock. There's no guarantee that everybody will be locking to the best clock. And so the failure that happens is potentially if your red and blue clocks are not locked together, one of them may well be signaling, I'm not a great clock, but you cannot guarantee your entire estate is either drifting with a bad clock or stuck with a good clock. There's absolutely no coherence in endpoint design that will enable that to happen. So you're better off removing that, and that is a more likely failure, right? I lose my antenna on one GM. Now what I got a split brain PTP distribution system. So if you think about what the failure modes are, you're better off delivering the same GMID to both amber and blue, red and blue. And then it doesn't matter which one the endpoint chooses.
Because you don't have full processing on red, full processing on blue. You have one processing that's taking your 2110, and you got the packet picker sitting in front of it for the network piece of it. And it properly designed, properly running network, technically you should be taking a 50% from red, 50% from blue, but it's not going to be every other packet, but it should be grabbing the packets from red or blue independently.
Yeah.
And
I mean,
you're going to drive things nuts if MAC addresses are swinging back and forth, domains are swinging back and forth. It's just nuts.
if you look at the financial trading type organizations, they do tend to deliver. They have a redundant PTP delivery, but they tend to have incredibly complex endpoints, and those endpoints
Yes.
are essentially, they are doing a very clever job of taking two sets of time, and when
Yes.
they're both accurate and when they're comfortable they're both accurate, they'll synthesize a more accurate time because they've got more samples. But when they don't believe they're the same, they will make a choice. They'll make the choice about the best clock, and that unfortunately we've not really done that in our industry yet.
No, because you have to look at those above the packet picker and grab PTP outside of the data that you're processing. And it's much more complex design, and video hasn't gotten anywhere close to that.
Excellent. I'm conscious of the times. I'm going to fire one more question in here. And the questions come basically timing in the world of 2110 in relation to PTP. Obviously, in our world, 2110-20 or -22 is only the active video. It doesn't start at pixel 0, line 0. Does it, Steve?
No, it does not. So the start of active video is the length of what your vertical interval would have been. PTP 0.0 is the same as black and burst, which is line 0, pixel 0. That's where PTP starts. But the first packet of active video is going to be the length of whatever your normal vertical interval is. So if it's like 1080i, it's going to be 21 lines. If it's 1080p, it's going to be 42 lines later. And that's where that sync needs to be. So those points 0, 0, that's the start of PTP. And lock at the start of where active video is. In this case, it started one line early, but like most things, there is a window within which you can lock. So most systems, if it didn't go out 21 lines, went to 20 lines. But there are tools out there that will look at this and tell you where things are at, and you just need to know the points in time that you need to be at for 1080i, 1080p, 720, for 3840, and lock to those specific points and make sure that that's where you're at.
I still find this amazing, Steve. We are now in the world of 2110, 2024, and the simplest way to explain active video is to show an analog waveform.
Yeah, it's where we started video. What can we say?
which goes, if you can hang around in this industry long enough, the wheel goes full circle and it comes back. It's just the infrastructure it's running on changes.
Yeah.
So, as we're highlighting there, for those of you who remember the term start of active video and end of active video, that's what we're talking about for the first packet arrival and your marker bit.
Yep.
So, and then there are tools, within the Leader and Fabrics product ranges that can allow you to see those displayed as any SDI engineer would remember, or still display the crosshair.
Yeah, there's 3 pieces of time you really should be looking at. First is PTP and Blackburst absolutely sync to each other, 0 on 0? Is your RTP packet time the length of the vertical interval? And then what you've got after RTP time is first packet time, which is what is the first packet that's actually read into the buffer. So it takes about 3 to 4 packets to get it read into the buffer. So that will be the first packet you'll actually be able to process. And I have seen many cases where people don't pay any attention to RTP at all. They put first packet right where it should be, but RTP is like 180 degrees out, essentially. And there's a lot of gear out there that is locking onto that RTP time, because per SMPTE, that is supposed to be the first packet of video that is processed in that frame is that RTP stamp for the entire frame. And a lot of people will look at that RTP stamp to find the first packet stamp. And if that RTP timestamp is wrong, you have no video.
I think the other great
everything's delivered absolutely perfect to you. PTP is perfect, transmission's perfect, but nothing comes up on the screen whatsoever. And you need tools to be able to look at those 3 timestamps to make sure they are accurate. And just a quick plug, and Leader's one of the only products on the market, or is the only waveform monitor that I'm aware of on the market that can actually use PTP to absolutely decode audio and video, or go free run, which means if you get a picture that only decodes about a third of the picture and then goes black on you, it's telling you your PTP is way out of time with where the video is and you're running out of buffer. You can change it to FIFO mode, basically equivalent of taking a waveform monitor and shutting off external sync and let it sync to the video data rather than the PTP data, and it'll present a picture to you and give you the tools now that you need to be able to troubleshoot.
Because there's a guarantee that if we can't see it in that mode, there are going to be downstream devices that are not going to display a picture as well, and you're going to have grief. So
I've seen it time and time again. We are hitting the top of the hour here.
We are indeed. So I think at this point we'll sort of wrap it up. As I said, we'd like to thank everybody for the questions that were asked. We've still got a few that we'll go through. As I said, we will get back to you. Thank you very much for this. I mean, it's certainly shown. I think
between Kevin, myself, and Gerard, we will answer every single question to you folks within a day or two. And every question you have will be answered. And a lot of these questions may give us something to actually come back with another session and actually focus a little more. So the 3 of us will have to talk.
So Gerard, thank you once again for joining us.
Thank you for the opportunity. Enjoyed it.
Always a pleasure, my friend. Always a pleasure.
As ever, it's really enlightening to see these questions, see where people are. You know, we've got people at various stages of their IP adventure, and I use the term adventure because, you know, the benefits of this are the only limitations with what you can do with workflows is your imagination once you've done this. You know, we're seeing people with some very, you know, creative workflows now with doing different things with audio. We're seeing ancillary data now really being, you know, utilized to its full potential that we could never do with SDI video. But get your foundation solid, and basically the world is your oyster. So thank you once again, Gerard. Steve, again, it's been a pleasure. Thank you very much for putting up with us. And to everybody, this will be available on our various YouTube channels as a catch-up. So we've covered a lot of detail. So if you need to go back and have a look at it, it will be posted as soon as the editor, if I can find him, can basically get his act together.
I wanted to thank Ryan also. He was great on the chat, answering a lot of technical questions. So a shout out to Ryan.
Yes, thank you, Ryan, for jumping in there.
Excellent.
All right. Thank you for coming to PTP Take 3. Great to see you all.
Hey, everybody, have a great evening, great morning, great afternoon. And we look forward to seeing you again.
Yeah, thank you very much, everybody.